Tonight, we're going to explore something that should be impossible. Somewhere out there in our galaxy, there are dead stars. Stars that have burned through all their fuel. Stars that have no engine left, no furnace, no source of energy keeping them alive. And by every intuition you have about how gravity works, these objects should keep collapsing. They should crush themselves down smaller and smaller and smaller until there's nothing left. But they don't. Something stops them. Something holds them up. And here's what's truly strange. The thing preventing their collapse has nothing to do with heat, nothing to do with energy, and nothing to do with any force you've ever experienced in your daily life. It comes from a law of quantum mechanics, and once you understand it, you'll never look at matter the same way again. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know, but probably haven't thought deeply about. Stars shine. You see them every night, scattered across the sky like pinpricks in a dark curtain. You've seen them your entire life. They seem permanent, fixed, eternal. Ancient humans thought they were exactly that. Unchanging lights attached to some kind of celestial sphere, rotating slowly overhead. But stars are not permanent. They are not eternal. Every single star you see when you look up at the night sky is a temporary object. Every one of them was born, every one of them is aging, and every one of them will eventually die. The sun, the star closest to us, the star that makes life on Earth possible, is no exception. It too will die. Not tomorrow, not next year, not in 1,000 years, but it will die. And what it leaves behind when it does is one of the strangest objects in the universe. But before we can understand what a star leaves behind, we need to understand what a star actually is while it's alive. Because the death of a star only makes sense when you understand the war that's been raging inside it for billions of years. A war between two fundamental forces that never stops, never pauses, never takes a break. A war that defines every moment of a star's existence from the instant it's born to the instant it dies. That war is between gravity and pressure. And everything we're going to explore tonight flows from understanding this single conflict. Let's begin with gravity, because gravity is where the story starts. Gravity is the most familiar force in the universe. You feel it right now, holding you to the surface of the Earth. It never pushes, it never repels, it only pulls. Every piece of matter in the universe attracts every other piece of matter. Your body is attracted to the chair you're sitting in, the chair to the floor to the earth to the sun. Gravity connects everything to everything else across the entire cosmos. It never turns off. There is no switch, no pause button, no way to shield yourself from it. It is always there, always pulling, always trying to bring things closer together. Now, gravity is a weak force in everyday life. You can overcome Earth's gravity just by standing up. You can jump and briefly leave the ground entirely. A small magnet can lift a paperclip against the gravitational pull of the entire planet. So gravity seems feeble, insignificant, easy to overcome, but that's only because you're small. When you have a lot of mass, when you gather together enormous quantities of matter, gravity becomes the most powerful force in the universe. Nothing else even comes close. Gravity built every planet, every star, every galaxy. Gravity shapes the large-scale structure of the entire cosmos. And gravity is the force that will eventually destroy every star that has ever existed or ever will exist. Here's how it works with stars. Imagine a cloud of gas floating in space, not a small cloud. An enormous cloud, perhaps dozens of light years across, containing enough gas to build dozens or even hundreds of stars. These clouds exist throughout our galaxy. They're called molecular clouds or sometimes nebulae, and they're made mostly of hydrogen, the simplest and most abundant element in the universe. Hydrogen makes up about 75% of all the normal matter in the cosmos. Helium makes up most of the rest, about 24%. Everything else, every other element on the periodic table, carbon, oxygen, iron, gold, uranium, all of it combined makes up less than 2%. The universe is overwhelmingly hydrogen and helium, and these are the raw materials from which stars are built. Now, these clouds of gas are not uniform. They have regions that are slightly denser than others. Maybe a nearby supernova explosion sent a shockwave through the cloud, compressing some regions. Maybe the gravitational influence of a passing star created a slight concentration. Whatever the cause, once a region of the cloud becomes dense enough, gravity takes over. The denser region starts pulling in surrounding gas. As more gas falls in, the region becomes even denser. As it becomes denser, its gravitational pull becomes stronger. As its gravitational pull becomes stronger, it pulls in even more gas. This is a runaway process. Once it starts, there's no stopping it. Gravity feeds on itself. More mass means more gravity, which means more mass, which means more gravity. The cloud begins to collapse. As the gas falls inward, it compresses. And when gas compresses, it heats up. This is a fundamental law of physics. If you've ever pumped air into a bicycle tire, you've felt the pump get warm. The same thing happens on a cosmic scale. As gravity compresses the collapsing cloud, the core gets hotter and hotter. The cloud contracts over hundreds of thousands of years, and the core temperature rises steadily. At first, it's a few hundred degrees, then a few thousand, then tens of thousands, then hundreds of thousands. The rising temperature creates pressure, thermal pressure, which pushes outward against gravity. This pressure slows the collapse, but doesn't stop it because gravity is still stronger. The cloud keeps contracting, the core keeps heating. When the core temperature reaches about 10 million degrees, something extraordinary happens. Something that changes everything. At 10 million degrees, hydrogen atoms are moving so fast that when they collide, they can overcome the electromagnetic repulsion between their positively charged nuclei and actually fuse together. This is nuclear fusion. Two hydrogen nuclei, which are just single protons, smash together with such violence that they stick. Through a series of steps, 4 hydrogen nuclei combine to form one helium nucleus. But here's the critical detail. One helium nucleus has slightly less mass than 4 separate hydrogen nuclei. The difference is tiny, less than 1%. But that tiny missing mass doesn't just disappear. It's converted into energy. This is Einstein's famous equation, E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is an enormous number, roughly 300,000 kilometers per second. When you square it, you get an even more enormous number. So even a tiny amount of mass, converted through this equation, produces a staggering amount of energy. Every single second, the sun converts about 600 million tons of hydrogen into about 596 million tons of helium. The missing 4 million tons of matter are converted into pure energy. 4 million tons of matter transformed into energy every second. That's the equivalent of about 90 billion 1 megaton nuclear bombs detonating every single second at the center of the sun. This has been going on for 4.5 billion years, and will continue for another 5 billion years or so. The numbers are almost impossible to grasp. The energy released by the sun in a single second is more than all the energy human civilization has produced in its entire history. And the sun is doing this every second of every minute of every hour of every day for billions of years. This energy, generated by nuclear fusion in the core, is what saves the star from gravitational collapse. The energy radiates outward from the core. It heats the gas surrounding the core. That hot gas exerts pressure, thermal pressure, pushing outward in all directions. And this outward pressure balances gravity's inward pull. The star reaches a state of equilibrium, a perfect balance between the force trying to crush it and the force trying to inflate it. Gravity pulls in. Thermal pressure pushes out. And the star hangs there, suspended in this balance, for millions or billions of years depending on its size. This equilibrium is called hydrostatic equilibrium, and it's one of the most important concepts in stellar physics. Think about what it means. The star is not static, it's not frozen. It's a dynamic balance between two enormous forces constantly fighting each other. If gravity increased slightly, the star would contract, compressing the core, heating it up, increasing fusion, producing more energy, creating more pressure, restoring the balance. If pressure increased, the star would expand, the core would cool, fusion would slow, pressure would drop, and gravity would pull things back in. The star self-corrects like a thermostat, automatically adjusting to maintain its equilibrium. This self-regulating mechanism keeps the star stable for extraordinarily long periods. The sun has been in this state of hydrostatic equilibrium for about 4.5 billion years. Every day for 4.5 billion years, gravity has been trying to crush the sun into a smaller and smaller ball. And every day for 4.5 billion years, the energy from nuclear fusion has produced enough pressure to prevent that from happening. Neither side has won. Neither side has lost. The battle has been a perfect stalemate for longer than Earth has existed. But here's what's crucial to understand. This balance depends entirely on fusion. Fusion is what generates the energy. The energy creates the heat. The heat creates the pressure. The pressure holds up the star. Without fusion, there is no energy. Without energy, there is no heat. Without heat, there is no pressure. Without pressure, gravity wins. Everything about a living star's stability comes from the fact that it's actively burning fuel, converting hydrogen into helium and releasing energy. Take away the fuel, and the entire structure collapses. The war ends. Gravity wins. It's as if the only thing holding up a building were a series of controlled explosions happening inside it, every second. The explosions push the walls outward just enough to counteract the weight of the building pressing inward. If the explosions stop, the building collapses instantly. That's essentially what a star is. A controlled thermonuclear explosion balanced against gravitational collapse. The explosion has been going on for billions of years, but it can't go on forever because the fuel is finite. Let me make this even clearer because it's fundamental to everything that follows. The pressure inside a normal star is thermal pressure. It depends on temperature. Hot gas pushes outward harder than cold gas. The hotter the gas, the faster the particles move. The faster they move, the harder they slam into their surroundings. The harder they slam, the more pressure they create. This is basic thermodynamics. It's why a balloon expands when you heat it. The gas molecules inside move faster, hit the walls of the balloon harder, and the balloon inflates. In a star, the gas molecules in the core are moving at incredible speeds because the temperature is millions of degrees. They're slamming into each other and into the surrounding gas with tremendous force, creating an enormous outward pressure that counteracts gravity. But this pressure requires temperature to exist. If the temperature drops, the pressure drops. If the pressure drops, gravity starts winning, and the temperature is maintained by fusion. It's all connected. Fusion creates energy, energy maintains temperature, temperature creates pressure, pressure fights gravity. Remove any link in that chain, and the whole thing falls apart. Now, let's talk about what the sun is actually made of and how its structure supports this ongoing battle. The sun isn't uniform. It has layers, each playing a different role in this constant struggle between collapse and expansion. At the very center is the core. This is where fusion happens. The core extends out to about 25% of the sun's radius, which means it occupies a relatively small fraction of the sun's total volume. But the core is where all the action is. The temperature here is about 15 million degrees Celsius. The pressure is about 265 billion times the atmospheric pressure on Earth's surface. The density is about 150 times the density of water, which means the core material is denser than most metals. Even though it's a gas, technically a plasma, it's compressed so tightly by gravity that it's denser than lead, denser than gold, denser than almost any solid material you've ever touched. In these extreme conditions, hydrogen nuclei are fusing into helium at a rate of about 600 million tons per second. Each fusion reaction releases a tiny burst of energy, but there are so many reactions happening every second that the total energy output is roughly 380 trillion watts. That's a 382 followed by 24 zeros. Watts of power continuously, without interruption, for billions of years. Surrounding the core is the radiative zone. This region extends from about 25% to about 70% of the sun's radius. Energy produced in the core travels outward through this zone, but it travels slowly. Not because the photons themselves move slowly. Photons always travel at the speed of light. But in the dense plasma of the radiative zone, photons can only travel a very short distance before they collide with a particle, get absorbed, and then get re-emitted in a random direction. The photon bounces around like a ball in a pinball machine, taking a random walk outward through the sun. On average, it takes a photon somewhere between 100,000 and 170,000 years to travel from the core to the surface of the sun. Think about that for a moment. The sunlight hitting your face right now was generated by fusion reactions that happened inside the sun's core, roughly 100,000 years ago or more. When that energy was first created, modern humans were just beginning to migrate out of Africa. Neanderthals still roamed Europe. Human civilization didn't exist yet. The energy bounced around inside the sun for all of human prehistory and most of human history before finally reaching the surface and streaming outward as visible light, reaching your eyes 8 minutes and 20 seconds after leaving the sun's surface. Above the radiative zone is the convective zone, extending from about 70% of the sun's radius to the surface. Here, energy is transported not by radiation, but by convection, the physical movement of hot gas. Hot plasma rises from the bottom of the convective zone toward the surface. When it reaches the surface, it radiates its energy into space, cools, and sinks back down to be reheated. This creates enormous convection cells, like bubbles in a pot of boiling water. The surface of the Sun, if you looked at it through a telescope with a proper solar filter, appears granulated, covered with these convection cells, each one about 600 miles across, each one rising and falling over the course of about 10 to 20 minutes. The surface of the Sun, called the photosphere, has a temperature of about 5,500 degrees Celsius. This is where the light we see is emitted. Above the photosphere are the chromosphere and the corona, the Sun's outer atmosphere. The corona is actually much hotter than the surface, reaching temperatures of 1 to 3 million degrees Celsius. Why the corona is so much hotter than the surface is one of the outstanding mysteries in solar physics. But for our purposes, what matters is the core, because the core is where the battle between gravity and pressure is won or lost. Now, here's something that most people don't realize about stars. Not all stars are the same. They vary enormously in size, mass, temperature, color, and lifespan. And all of these properties are determined primarily by one thing: mass. How much stuff the star contains when it's born. A star's mass determines almost everything about it. How hot it burns, how brightly it shines, what color it appears, how long it lives, and most importantly for our story, how it dies. Low-mass stars, those with less than about half the mass of the Sun, are small, cool, and red. They're called red dwarfs, and they're the most common type of star in the galaxy. About 70% of all stars are red dwarfs. They burn their hydrogen fuel very slowly because the gravitational pressure on their cores is relatively modest, so the fusion rate is low. Because they burn fuel slowly, they live for an extraordinarily long time. A red dwarf with about 10% of the Sun's mass could shine for 10 trillion years or more. The universe is only 13.8 billion years old. 10 trillion years is more than 700 times the current age of the universe. No red dwarf that has ever formed has ever died of old age. Every red dwarf that has ever existed is still shining today. They are the most patient objects in the cosmos. Stars like the Sun, those with roughly half to about 8 times the Sun's mass, are medium-sized stars. They burn hotter and brighter than red dwarfs, but they also burn through their fuel faster. The Sun will live for about 10 billion years total. It's already used up about 4.5 billion years of that. Stars slightly more massive than the Sun live shorter lives. A star with twice the Sun's mass might live only about 2 billion years. A star with 5 times the Sun's mass might live only about 100 million years. There's a clear pattern here. The more massive the star, the shorter its life. This seems counterintuitive at first. You might think a more massive star has more fuel, so it should last longer. And it does have more fuel, but it burns that fuel at a dramatically higher rate. A star with 10 times the Sun's mass doesn't burn its fuel 10 times faster. It burns it roughly 10,000 times faster. The increase in fuel consumption far outpaces the increase in fuel supply. More massive stars live shorter lives, always. The most massive stars, those with more than about 8 times the Sun's mass, are spectacular but short-lived. They're hot, blue, and incredibly luminous. A star with 50 times the Sun's mass might shine 1,000,000 times brighter than the Sun, but it will exhaust its fuel in just a few million years. These stars live fast and die young. They burn through their fuel so quickly that their lives are measured in millions of years. not billions. By stellar standards, they exist for the blink of an eye. Born in a burst of light and gone before most other stars have even finished their adolescence. But here's the thing that matters for our story. Regardless of size, regardless of mass, regardless of how long they live, every star faces the same fundamental problem. Fuel is finite. The hydrogen in the core is being consumed. It's being converted into helium. And once it's converted, it's gone. You can't unfuse helium back into hydrogen. The process is one way. Every fusion reaction uses up a tiny amount of fuel and replaces it with ash. Helium is the ash of hydrogen fusion. Over time, the core fills up with helium while the supply of hydrogen decreases. The star is slowly eating itself from the inside out. For the Sun, this process is about halfway complete. The core has converted a significant fraction of its original hydrogen into helium over the past 4.5 billion years. The composition of the core has changed. It's no longer pure hydrogen. It's a mixture of hydrogen and helium, with the helium fraction steadily increasing. And as the hydrogen fraction decreases, the fusion rate must adjust to maintain equilibrium. The core gradually contracts slightly, heating up a little, compensating for the reduced fuel supply by burning what's left more intensely. The Sun today is actually about 30% brighter than it was when it first formed 4.5 billion years ago. It's been getting slowly, steadily brighter as it ages. This has implications for Earth's climate and for life, but that's a different story. What matters right now is this: the fuel will run out. Not immediately, not soon by human standards, but inevitably. The hydrogen in the core will be consumed. And when that happens, the fusion reactions that have sustained the star for billions of years will stop. The engine that has been generating energy, maintaining temperature, creating pressure, fighting gravity will shut down. The balance that has held the star steady for billions of years will be broken. And gravity, which has been patiently waiting, pulling inward every second of every day for billions of years, will finally begin to win. This is the moment everything changes. The moment when a star's life story takes a dramatic turn. Because what happens next depends entirely on the star's mass. The most massive stars will go out in spectacular explosions, supernovae that briefly outshine entire galaxies. But for stars like the Sun, for average, ordinary, medium-mass stars, the death is quieter but no less strange. These stars don't explode. Instead, they go through a series of transformations that would seem impossible if we didn't have the physics to explain them. They swell to enormous sizes, engulfing their inner planets. They shed their outer layers into space, creating some of the most beautiful objects in the universe. And then they leave behind something truly extraordinary. A tiny, incredibly dense remnant. Dead core with no engine, no furnace, no source of new energy. An object so dense that a teaspoon of its material would weigh several tons on Earth. That object is a white dwarf. And here's the question that should immediately come to mind once you know what a white dwarf is. If there's no fusion happening inside it, if there's no energy being generated, if there's no heat-driven pressure pushing outward, then why doesn't gravity just keep crushing it? What's holding it up? Because gravity hasn't gone anywhere. Gravity is still there, still pulling, still trying to compress this dead stellar core into something smaller. The force that has been trying to collapse this star for its entire life hasn't stopped just because the star died. If anything, the situation is worse now because the star's defense fusion-powered thermal pressure is gone. The shield is down. The weapon that fought gravity to a stalemate for billions of years has been removed. So gravity should win. The remnant should keep collapsing, getting smaller and smaller and denser, without limit. But it doesn't. Something stops it. Something holds it up. And that something is not heat, not energy, not anything you would expect. It's something far stranger, something rooted in the deepest laws of quantum mechanics. Something that has nothing to do with temperature at all. Understanding what that something is, understanding why this dead star refuses to collapse any further, is one of the most remarkable stories in all of physics. And it begins with understanding exactly how a star like the Sun meets its end. The Sun has about 5 billion years of hydrogen fuel left in its core. That sounds like an eternity, and by human standards it is. 5 billion years ago, Earth had just formed. Life didn't exist yet. The planet was a molten ball of rock being bombarded by asteroids. 5 billion years is an almost incomprehensible stretch of time. But in the life of the universe, it's not that long. And for the Sun, it's the beginning of the end. Because once that hydrogen is gone, the Sun's story enters its final chapter. And that chapter is stranger than anything that came before. Let's walk through what happens, step by step, because the details matter and they're going to set up one of the most extraordinary puzzles in physics. As the Sun burns through its hydrogen fuel over the next several billion years, the core gradually changes composition. Right now, the core is a mixture of hydrogen and helium, with hydrogen still dominant. But with every passing second, 600 million tons of hydrogen are being converted into helium. That helium accumulates in the core like ash building up in a fireplace. Over billions of years, the core becomes increasingly helium-rich. The hydrogen that remains gets pushed outward, forming a thin shell around the growing helium core. Eventually, the core runs out of hydrogen entirely. There's still hydrogen in the layers above the core, but the core itself, the region where temperatures and pressures are high enough for fusion, has been converted almost entirely to helium. And this is where the trouble begins. Helium doesn't fuse at the same temperatures as hydrogen. Hydrogen fusion requires about 10 million degrees. Helium fusion requires about 100 million degrees. That's 10 times hotter. The reason is electromagnetic repulsion. Helium nuclei have 2 protons each, compared to hydrogen's 1. More protons mean more positive charge. More positive charge means stronger electromagnetic repulsion between nuclei. To overcome that stronger repulsion and force helium nuclei close enough to fuse, you need much higher velocities, which means much higher temperatures. At 10 or 15 million degrees, hydrogen can fuse, but helium cannot. The helium just sits there, inert, doing nothing. It's like having a pile of wet logs in a fireplace. You know they contain energy, you know they could burn, but you can't ignite them with a match. You need something much hotter. So what happens when the core fills up with helium that can't fuse? Fusion in the core stops. Not gradually, not slowly. It stops because there's nothing left to fuse at the temperatures available. The hydrogen is gone and the helium needs temperatures the core hasn't reached yet. The engine shuts down, and the moment fusion stops in the core, the thermal pressure that was holding up the star begins to drop. Gravity, which has been waiting patiently for billions of years, starts to gain the upper hand. The core begins to contract. But here's what's fascinating. The star doesn't just quietly collapse. The contraction of the core actually triggers something unexpected. As the helium core contracts under gravity, it heats up. Remember, compressing gas increases its temperature. The core gets hotter and hotter as it shrinks. And while the core itself can't fuse helium yet, because it hasn't reached 100 million degrees, the region just outside the core, the thin shell of hydrogen that still surrounds it, gets compressed and heated as well. This hydrogen shell reaches temperatures and pressures sufficient for fusion. A new round of hydrogen fusion ignites, not in the core this time, but in a shell wrapped around the core. Shell hydrogen burning, as astronomers call it, is actually more vigorous than the core burning that preceded it. The shell is being compressed by the weight of everything above it, and the collapsing core beneath it is providing additional heat. The fusion rate in the shell skyrockets. The energy output increases dramatically, and this enormous flood of new energy has to go somewhere. This is where the star transforms into something almost unrecognizable. The energy pouring out of the hydrogen-burning shell pushes the outer layers of the star outward. The star begins to expand. Not a little, not modestly. It expands enormously. The outer envelope of the star inflates like a balloon, growing larger and larger over millions of years. As the outer layers expand, they cool. Cooler gas emits redder light. The star, once yellow-white like the sun, becomes redder and redder as its surface temperature drops. The star has become a red giant. The numbers here are staggering. When the sun becomes a red giant in about 5 billion years, it will expand to roughly 100 to 200 times its current diameter. Right now, the sun is about 864,000 miles across. As a red giant, it will be somewhere around 100 million to 200 million miles across. That's enormous. The distance from the sun to Earth is about 93 million miles. As a red giant, the sun's surface will extend outward so far that it will engulf Mercury. It will engulf Venus. It will either engulf Earth entirely or come so close that our planet's surface will be stripped and sterilized, the oceans boiled away, the atmosphere blown into space, and the rocky surface heated to thousands of degrees. Whether Earth is physically consumed or merely destroyed from close range, the result is the same. Our planet will cease to exist as anything recognizable. Meanwhile, deep inside this bloated red giant, the helium core continues to contract and heat. The core is getting denser and hotter, crushed by the weight of the enormous envelope above it. In a star like the sun, the core eventually reaches the critical temperature, about 100 million degrees. At this point, helium fusion ignites. 3 helium nuclei combine to form one carbon nucleus through a process called the triple alpha process. This process also produces some oxygen when a carbon nucleus captures an additional helium nucleus. The ignition of helium fusion is actually quite dramatic in sun-like stars. It happens in a sudden event called the helium flash. The core has become so compressed during its long contraction that it's entered a peculiar state of matter governed by quantum mechanics. And when helium fusion finally ignites, it happens almost explosively. The energy release in the core during the helium flash is enormous, briefly exceeding the total luminosity of the entire Milky Way galaxy. But this energy is absorbed by the core itself and doesn't reach the surface. From the outside, you wouldn't see anything dramatic. The helium flash is hidden deep within the star, a secret internal convulsion. After the helium flash, the core settles into a new equilibrium. Helium is fusing into carbon and oxygen in the core. Hydrogen is still fusing in the shell above. The star adjusts its structure, shrinking somewhat from its most extended red giant size. and enters a phase of relatively stable helium burning. But this phase doesn't last long. Helium burning is far less efficient than hydrogen burning. The star burns through its helium fuel much faster than it burned through its hydrogen. While hydrogen burning in the core lasted billions of years, helium burning in the core lasts only about 100 million years or so. That's roughly 1/100th as long. In cosmic terms, helium burning is brief, a short chapter in a long story. And then the same problem repeats. The helium in the core runs out. The core is now made of carbon and oxygen, the products of helium fusion. Carbon and oxygen can fuse, but only at temperatures of about 500 million to 1 billion degrees. For a star like the Sun, the core will never reach these temperatures. The Sun simply doesn't have enough mass. Its gravity isn't strong enough to compress the core to the extreme densities and temperatures needed for carbon fusion. This is the end of the line. For a star with the Sun's mass, nuclear fusion stops here. The core cannot go any further. There's fuel available in principle. Carbon and oxygen could theoretically fuse, but the conditions required are forever beyond reach. The engine has burned its last fuel. The furnace has gone out for the final time. What happens to the outer layers of the star is beautiful. As the star goes through its final stages of evolution, pulsating and adjusting to the changing conditions in its interior, the outer layers become increasingly loosely bound. The star has expanded so much that its surface gravity is weak. Material at the outer edge of the star is barely held on. Pulsations in the star, driven by the unstable nuclear burning in shells, send waves of energy outward through the envelope. These pulsations grow stronger over time. Eventually, the outer layers of the star are expelled entirely. Not in a violent explosion, but in a series of gentle exhalations. The star breathes its outer layers into space over the course of tens of thousands of years. This expelled gas forms an expanding shell around the dying star, a glowing cloud of gas illuminated by the hot core that remains behind. This cloud is called a planetary nebula, a misleading name that has nothing to do with planets. The term was coined in the 18th century by William Herschel, because these objects looked vaguely round and greenish through early telescopes, somewhat like the planet Uranus. The name stuck, even though we now know they're nothing like planets. Planetary nebulae are among the most beautiful objects in the universe. The Hubble Space Telescope has captured stunning images of them. The Ring Nebula in the constellation. Lyra shows a nearly perfect ring of glowing gas surrounding a tiny hot star at its center. The Cat's Eye Nebula displays intricate concentric shells and jets of gas forming complex patterns. The Helix Nebula, sometimes called the Eye of God because of how it appears in photographs, is an enormous cloud of gas about 2.5 light years across, slowly dissipating into the surrounding space. Every one of these nebulae was once the outer layers of a star like the Sun. Every one of them represents a star that ran out of fuel, shed its atmosphere, and left its core exposed to the vacuum of space. And that core, that exposed remnant sitting at the center of the expanding planetary nebula, is a white dwarf. Let me describe what this object actually is, because it's truly extraordinary. When the outer layers have been blown away and the nebula has dispersed into the surrounding interstellar medium, which takes about 20,000 years or so, what remains is just the core. The carbon and oxygen core that could never get hot enough to fuse. This core contains a significant fraction of the star's original mass, typically between about 1/2 and 3/4 of the Sun's mass, depending on how much material was lost during the red giant and planetary nebula phases. For a star that started with about the same mass as the Sun, the white dwarf remnant contains roughly half a solar mass, maybe a bit more. Now here's where things get remarkable. That half a solar mass of material, which is still an enormous amount of matter, roughly 165,000 times the mass of the Earth, is compressed into an object about the size of Earth itself. Think about that carefully. Take something with the mass of a star, or rather half the mass of a star, and compress it into a volume the size of a planet. The result is density beyond anything you've ever experienced or could possibly experience in everyday life. A typical white dwarf has a diameter of roughly 7,000 to 14,000 miles. Earth's diameter is about 7,900 miles. So a white dwarf is comparable in my mind size to Earth, maybe a bit smaller, maybe a bit larger depending on its exact mass. But while Earth has a mass of about 6 trillion kilograms, a white dwarf with half the Sun's mass has a mass of about 1 million trillion kilograms. That's roughly 165,000 times more massive than Earth, packed into a similar volume. The density is almost incomprehensible. A typical white dwarf has an average density of about 1 million grams per cubic centimeter. 1 million grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter. Iron has a density of about 7.9 grams per cubic centimeter. Gold has a density of about 19.3 grams per cubic centimeter. Osmium, the densest naturally occurring element on Earth, has a density of about 22.6 grams per cubic centimeter. A white dwarf is roughly 44,000 times denser than osmium. 44,000 times denser than the densest element you can hold in your hand. The classic way to illustrate this density is with the teaspoon analogy. If you could scoop up a teaspoon of white dwarf material and bring it to Earth, that teaspoon would weigh about 5.5 tons. A teaspoon. 5.5 tons. That's roughly the weight of a large elephant, concentrated into a volume smaller than your thumb. If you set that teaspoon on a table, it would crash straight through the table, through the floor, through the foundation, and keep going into the ground. Nothing in your everyday experience could support something that dense. The strongest steel beam would crumple under a handful of white dwarf material. The surface gravity on a white dwarf is about 100,000 to 300,000 times stronger than the gravity on Earth's surface. If you somehow stood on the surface of a white dwarf, and you obviously couldn't because you'd be instantly crushed and vaporized, but hypothetically you'd weigh 100,000 to 300,000 times your Earth weight. A person weighing 150 pounds on Earth would weigh somewhere around 15 million to 45 million pounds on a white dwarf. The gravitational force would flatten you into a thin film of atoms in a fraction of a second. Now let's talk about what a white dwarf is doing, or rather, what it isn't doing, because this is the key to the puzzle. A white dwarf is not generating energy. There is no nuclear fusion happening in its interior. The carbon and oxygen core never reach the temperatures needed for further fusion, and now that the outer layers have been expelled, there's nothing left to compress the core further through ordinary means. The furnace is cold, the engine is off, the reactor has shut down, there's no new energy being produced anywhere inside the object. So why is a white dwarf hot? Why does it glow? Why can we see it? Because it's radiating stored heat. When the white dwarf first forms, When it's first exposed after the planetary nebula clears, its surface temperature is extremely high, often above 100,000 degrees Celsius. Some newly formed white dwarfs have surface temperatures exceeding 200,000 degrees. This is residual heat, leftover thermal energy from the billions of years of nuclear fusion that occurred when the star was alive, plus the heat generated by gravitational contraction during the star's final stages. The white dwarf is like a coal pulled from a fire. The fire is out, but the coal is still glowing with stored heat. And just like a coal, the white dwarf will slowly cool over time, radiating its heat into space. But the cooling process is extraordinarily slow. The white dwarf contains a tremendous amount of stored heat in a very compact volume, and it can only radiate that heat from its relatively small surface. The cooling takes billions of years. A white dwarf that forms today will still be warm and visible billions of years from now. In fact, the universe is only 13.8 billion years old, and theoretical calculations show that no white dwarf has yet had time to cool completely. The oldest white dwarfs in the galaxy, those that formed from the first generation of sun-like stars, have cooled to surface temperatures of only about 3,000 to 4,000 degrees Celsius. They're dim and red, but they're still glowing. They haven't had time to go dark. Eventually, after trillions of years, a white dwarf will cool to the point where it no longer emits visible light, becoming a black dwarf. But no black dwarfs exist yet because the universe isn't old enough. Every white dwarf that has ever formed is still out there, still glowing, still slowly releasing the heat it inherited from its former life. This is worth pausing on because it tells you something profound about these objects. White dwarfs are patient. They are the most patient objects in the cosmos. They sit in space, not doing anything, not burning anything, not fusing anything, just slowly, imperceptibly cooling. They will outlast almost everything else in the universe, long after the last hydrogen-burning stars have died, long after the galaxies have faded. White dwarfs will still be out there, dim but persistent, the last glowing embers of a universe that was once filled with starlight. White dwarfs are also incredibly common, because every star with mass between about half the sun's mass and roughly 8 times the sun's mass will end its life as a white dwarf, and this range covers the vast majority of all stars. White dwarfs are everywhere. About 97% of all stars in the Milky Way will eventually become white dwarfs. Astronomers estimate that there are already around 10 billion white dwarfs in our galaxy alone. 10 billion dead stellar cores, each one roughly the size of Earth, each one containing the mass of a star, scattered throughout the Milky Way. Some are young and hot, blazing with ultraviolet radiation. Some are ancient and cool, barely visible even with powerful telescopes. But all of them share the same fundamental nature. They are the compressed cores of dead stars, no longer powered by fusion, slowly cooling in the darkness. Sirius B, the companion star to Sirius, the brightest star in the night sky, is a white dwarf. It was actually the first white dwarf ever discovered, identified in the mid-1800s. Sirius B has roughly the same mass as the Sun compressed into a sphere slightly smaller than Earth. Its surface temperature is about 25,000 degrees, which makes it a relatively young and hot white dwarf. It's still glowing brightly, but it will never generate new energy. It's living off its savings, spending down its thermal reserves. and it will keep doing so for billions upon billions of years. The nearest known white dwarf to Earth is Sirius B at about 8.6 light years away. Van Manen star at 14.1 light years, and Procyon b at 11.5 light years are others nearby. Dead stars scattered among the living ones, quietly fading in our cosmic backyard. Now, let's return to the question that has been building throughout this entire discussion. The question that should be nagging at you if you've been following the logic carefully. We established that a normal, living star is held up by thermal pressure. Hot gas pushes outward and balances gravity pulling inward. We established that this thermal pressure depends on temperature, and that the temperature is maintained by nuclear fusion. We established that when fusion stops, the source of thermal pressure disappears. A white dwarf has no nuclear fusion. None. Zero. The engine is permanently off. There was nothing generating new energy inside this object. It's just sitting there, slowly cooling, radiating away its stored heat into the void of space. Every day it's a little cooler than it was the day before. Every century it's dimmer than it was the century before. Over billions and trillions of years, it will cool down to the temperature of the surrounding space, essentially to absolute zero or close to it. But here's what should trouble you. As the white dwarf cools, its thermal pressure should decrease. In a normal star, lower temperature means lower pressure. Lower pressure means gravity starts winning. Gravity contracts the star. In a living star, this contraction would heat the core, increase fusion, and restore equilibrium. But a white dwarf has no fusion to restart. There's no mechanism to regenerate the thermal pressure. The temperature drops, the thermal pressure drops, and gravity should keep squeezing. The object should keep contracting, getting smaller and smaller and denser as it cools. By the time it reaches near absolute zero, trillions of years from now, it should have been crushed to almost nothing. A point of infinite density, or at the very least, something far smaller than Earth-sized. But this doesn't happen. White dwarfs don't keep contracting as they cool. They maintain their size. A white dwarf that forms today at 100,000 degrees will be essentially the same diameter when it cools to 10,000 degrees, to 1,000 degrees, to 100 degrees, to near absolute 0 trillions of years from now. The cooling doesn't cause further collapse. The object is stable at its current size regardless of its temperature. Gravity is still pulling inward, just as relentlessly as ever, and yet the white dwarf doesn't budge. Something is holding it up. Something that doesn't weaken as the temperature drops. Something that has nothing to do with heat. This is genuinely bizarre if you think about it from the perspective of classical physics. In classical physics, the only thing that fights gravity inside a ball of gas is thermal pressure, the random motion of hot particles pushing outward. Take away the heat, and there's nothing left to fight. Gravity wins. End of story. And yet, white dwarfs exist. They're real. We can observe them. We can measure their sizes and masses and temperatures. We can watch them cool over time. And they don't collapse. Whatever's holding them up, it isn't heat. It isn't energy from fusion. It isn't any kind of engine or power source. It's something else entirely. Something that classical physics cannot explain. The answer lies in quantum mechanics, in one of the strangest and most counterintuitive principles in all of physics. A principle that says that particles of matter have a fundamental identity, a quantum property that prevents them from being compressed beyond a certain point. Regardless of how much force you apply, regardless of temperature, regardless of whether any energy is being generated. This quantum effect creates a pressure, a resistance to compression that has absolutely nothing to do with heat. It doesn't weaken when the temperature drops. It doesn't require energy to sustain. It is a consequence of the fundamental nature of matter itself, built into the laws of quantum mechanics at the deepest level. This pressure is what holds up every white dwarf in the universe. It's what prevents gravity from finishing the job it started billions of years ago when the star first began to die. It's what allows a dead stellar core to sit in space for trillions of years, cooling from blazing hot to absolute cold, without collapsing by even a fraction of an inch. The shield that protects a white dwarf is not made of fire. It's not made of energy. It's made of quantum law. And understanding how that law works, understanding why electrons refuse to be pushed too close together, is one of the most beautiful and profound ideas in all of science. It's a story about identity, about the fundamental nature of particles, about the rules that govern the smallest things in the universe, reaching up to determine the fate of the largest. And it changes everything about how we understand what matter really is, and what it can do when pushed to extremes that exist nowhere else in our everyday experience. To understand what holds up a white dwarf, we need to leave the world of stars for a moment and go somewhere much smaller. We need to go inside matter itself, down to the level of atoms, down to the level of the particles that make up atoms. Because the answer to our puzzle doesn't come from astrophysics. It comes from quantum mechanics, the branch of physics that governs the behavior of the smallest things in the universe. And what quantum mechanics tells us about particles is so strange, so counterintuitive, so fundamentally different from anything in our everyday experience that when physicists first discovered these rules in the early 20th century, many of them refused to believe what the mathematics was telling them. But the mathematics was right, and the consequences of those rules reach far beyond the subatomic world. They reach all the way up to the scale of dead stars, determining whether a stellar remnant the size of Earth collapses into oblivion or holds its ground against gravity forever. Let's start with atoms. Everything around you is made of atoms. The chair you're sitting in, the air you're breathing, the screen or device you're using right now, your own body, all of it is atoms. And atoms are mostly empty space. This is one of those facts that sounds like an exaggeration but isn't. An atom consists of a tiny nucleus at the center made of protons and neutrons surrounded by a cloud of electrons. The nucleus is incredibly small compared to the atom as a whole. If an atom were the size of a football stadium, the nucleus would be about the size of a marble sitting at the center of the field. Everything else, the vast majority of the atom's volume, is occupied by the electron cloud. But even saying the electrons occupy that space is misleading, because electrons aren't little balls orbiting the nucleus like planets orbit the sun. That picture, the one you probably learned in school, is wrong. Electrons in an atom don't have definite positions. They exist as probability distributions, smeared out clouds of likelihood. You can't say exactly where an electron is at any given moment. You can only say where it's likely to be. This is one of the fundamental features of quantum mechanics. At the subatomic scale, particles don't behave like tiny billiard balls. They behave like waves. They have wave-like properties that determine where they can and can't exist. And these properties lead to rules that have no parallel in our everyday experience. Now, here's where things get interesting for our white dwarf story. There are two fundamental types of particles in the universe. Physicists call them fermions and bosons. The difference between them is one of the most important distinctions in all of physics, and it determines the fate of dead stars. Bosons are particles that carry forces. Photons are bosons. They carry the electromagnetic force. Gluons are bosons. They carry the strong nuclear force. The key property of bosons is that they're sociable. Multiple bosons can occupy the same quantum state at the same time. You can stack as many photons as you want into the same place with the same energy and the same properties. They don't mind. They'll happily pile on top of each other. This is actually why lasers work. A laser produces coherent light, meaning all the photons are in the same quantum state, traveling in the same direction with the same frequency. Bosons allow this kind of stacking. Fermions are different, profoundly different. Fermions are the particles that make up matter. Electrons, protons, neutrons, and the quarks inside them are all fermions. Everything made of matter is made of fermions. And fermions have a property that bosons don't. A property that changes everything. Fermions refuse to share. Two fermions of the same type cannot occupy the same quantum state at the same time. Ever. Under any circumstances. No matter how much force you apply, no matter how much pressure you exert, no matter how high the temperature or how extreme the conditions, you cannot force two identical fermions into the same quantum state. This rule is absolute. It has no exceptions. It has never been violated in any experiment ever conducted. It is one of the most ironclad laws in all of physics. This rule is called the Pauli exclusion principle, named after the Austrian physicist Wolfgang Pauli, who formulated it in 1925. Pauli was trying to explain the structure of atoms, specifically why electrons in an atom arrange themselves in shells rather than all piling into the lowest energy state. Classical physics couldn't explain this. If electrons were just negatively charged particles attracted to the positively charged nucleus, they should all fall to the lowest possible energy level, as close to the nucleus as they could get. But they don't. Electrons fill up energy levels one by one. The first energy level can hold 2 electrons, the second can hold 8, the third can hold 18. Each level fills up before the next one starts. Pauli realized that this behavior only made sense if no 2 electrons could share the same quantum state. Each quantum state can hold exactly 1 electron. Once a state is filled, the next electron must go into a different state, usually a higher energy one. This is why atoms have the structure they do. This is why the periodic table has the shape it has. This is why chemistry works the way it does. The Pauli exclusion principle determines the arrangement of electrons in atoms, which determines how atoms bond with each other, which determines the properties of molecules, which determines the properties of everything made of molecules. Every material property you've ever encountered, the hardness of steel, the flexibility of rubber, the transparency of glass, the conductivity of copper, all of it traces back ultimately to the Pauli exclusion principle governing how electrons arrange themselves in atoms. Now let's think about what this means when you start squeezing matter. In normal conditions, the atoms in a solid or a gas are spaced far enough apart that the Pauli exclusion principle isn't particularly noticeable at the macroscopic scale. The electrons in each atom occupy their own quantum states within their own atom, and the atoms are far enough apart that the electron clouds don't significantly overlap. There's plenty of quantum real estate for everyone. But what happens when you compress matter? What happens when you squeeze it so hard that the atoms are forced closer and closer together? The electron clouds start to overlap. Electrons from different atoms are now sharing the same region of space. And this is where the Pauli exclusion principle starts to matter enormously. Because as you compress the material, you're reducing the volume available to the electrons. You're shrinking the space in which they can exist. And since each electron must occupy a unique quantum state, and the number of available low-energy states in a given volume is limited, electrons are forced into higher and higher energy states as the volume decreases. Imagine a room full of people where each person must stand in their own square on the floor. No sharing. If the room is large, there are plenty of squares, but now the room starts shrinking. As squares disappear, some people have to move to higher positions. They stand on chairs, then tables, then shelves. They're pushed into higher and higher energy states because all the low positions are taken. The more you compress the room, the higher some people have to go. As they're forced upward, they push back against the walls harder. The harder you squeeze, the harder they resist. This is not a perfect analogy, but it captures the essential idea. When you compress a gas of fermions, the Pauli exclusion principle forces particles into higher energy states. These higher energy particles exert a pressure, a resistance to further compression. And this pressure has a remarkable property. It doesn't depend on temperature. It depends only on density and the number of fermions packed into a given volume. This is the crucial distinction. In a normal star, the pressure that fights gravity is thermal pressure. It comes from the random motion of hot particles. If the star cools, the particles slow down, the pressure drops, and gravity gains ground. Thermal pressure requires heat to exist. But the pressure created by the Pauli exclusion principle is different. It arises not from heat, but from the quantum mechanical identity of fermions. Even if you cooled the material to absolute zero, even if every particle had the lowest energy it could possibly have, the electrons would still be spread across many different quantum states, because they can't all share the lowest state. The electrons at the top of the energy distribution, the ones forced into the highest occupied states, would still be moving with significant velocity. They would still be exerting pressure at absolute zero. This pressure doesn't vanish. It persists. It is a permanent, temperature-independent resistance to compression that arises purely from the nature of fermions. This pressure is called electron degeneracy pressure. The word degeneracy here has a specific meaning in physics. It doesn't mean degraded or deteriorated. In quantum mechanics, a degenerate gas is one where the quantum effects of the Pauli exclusion principle dominate the behavior of the particles, rather than thermal effects. In a normal gas, particles move around randomly with speeds determined by the temperature. Hot gas has fast particles, cold gas has slow particles. The behavior of the gas is determined by its temperature. But in a degenerate gas, the particles are packed so tightly that the Pauli exclusion principle forces many of them into high energy states, regardless of the temperature. Even at low temperatures, these particles are moving fast because quantum mechanics demands it. The gas behaves differently from a normal gas. Its pressure depends on density rather than temperature. It's a fundamentally different kind of matter, obeying fundamentally different rules. And this is exactly what the interior of a white dwarf is. The matter inside a white dwarf has been compressed to such extreme densities that the electrons have become degenerate. The atoms have been crushed so tightly together that they've lost their individual identities. In normal matter, electrons are bound to specific atoms. They orbit specific nuclei. Each atom maintains its own electron cloud. But at the densities inside a white dwarf, roughly 1 million grams per cubic centimeter, the atoms have been completely stripped. The electrons have been torn free from their nuclei. The nuclei, mostly carbon and oxygen, form a dense lattice structure, something like a crystalline solid. And the electrons form a degenerate gas that permeates this lattice, flowing freely between the nuclei, no longer belonging to any individual atom. These free electrons are the key to the white dwarf's survival. They are the shield that holds gravity at bay. As gravity tries to compress the white dwarf further, it tries to squeeze the electrons into a smaller volume. But the Pauli exclusion principle says no. The electrons cannot all be forced into the same quantum state. As the volume decreases, electrons must occupy higher and higher energy states. These high-energy electrons move faster and exert more pressure. The pressure increases as the density increases, pushing back against gravity. And crucially, this pushback doesn't weaken when the white dwarf cools. The temperature of the white dwarf can drop from 100,000 degrees to 10,000 degrees to 1,000 degrees to 10 degrees to 1 degree to a fraction of a degree above absolute zero. It doesn't matter. The electron degeneracy pressure remains. The electrons are still packed just as tightly. They're still forced into high-energy quantum states by the exclusion principle. They still push back against gravity with the same force. This is profoundly different from how a normal star works. In a normal star, if you turned off the fusion and let the star cool, it would collapse. The thermal pressure would fade as the temperature dropped, and gravity would crush the star smaller and smaller. But a white dwarf doesn't work that way. Its support mechanism is decoupled from its temperature. It can cool to absolute zero, and it will still maintain its size. The quantum mechanical pressure holding it up is permanent, eternal, unyielding. It doesn't need fuel. It doesn't need energy. It doesn't need anything. It simply exists. A consequence of the fundamental rules governing the identity of electrons. Let me try to make this even more concrete. Inside a white dwarf, the electron degenerate gas has properties that would seem bizarre by everyday standards. The electrons at the top of the energy distribution, the ones in the highest occupied quantum states, are moving at a significant fraction of the speed of light. Not because the white dwarf is hot, although newly formed white dwarfs are quite hot, but because quantum mechanics demands it. Even if you could somehow cool a white dwarf to absolute zero, which would take trillions of years and has never actually happened, the fastest electrons inside it would still be moving at a significant fraction of light speed. They have to be. There's nowhere else for them to go. All the lower energy states are occupied. They're stuck in high energy states, moving fast, slamming into each other and into the surrounding nuclei with tremendous force, creating the pressure that supports the star. This is sometimes described as quantum pressure or Fermi pressure, named after the physicist Enrico Fermi, who developed much of the statistical framework describing how fermions behave in dense systems. Fermi showed that in a degenerate gas, there's a well-defined maximum energy level called the Fermi energy. All quantum states below this energy are filled. All states above it are empty, at least at absolute zero. The Fermi energy depends on the density of the fermion gas. Higher density means a higher Fermi energy, which means faster moving particles at the top of the distribution, which means more pressure. This mathematical framework allows physicists to calculate the exact pressure inside a white dwarf, given its density. And when they do the calculation, the numbers come out exactly right. The electron degeneracy pressure at the densities found inside white dwarfs is precisely what's needed to balance gravitational collapse. Let me put some numbers on this so you can appreciate the scale. In the core of a typical white dwarf, the density is about 10 million grams per cubic centimeter or higher. At this density, the Fermi energy of the electrons is about 300,000 electron volts. For comparison, the thermal energy of particles at room temperature is about 1/40th of an electron volt. At the surface temperature of a newly formed white dwarf, about 100,000 degrees, the thermal energy is about 8 electron volts. The Fermi energy is still tens of thousands of times higher than the thermal energy. This tells you that the quantum effects completely dominate. The behavior of the electrons inside a white dwarf is determined almost entirely by the Pauli exclusion principle and almost not at all by the temperature. The temperature is essentially irrelevant. It's like a rounding error in a calculation dominated by much larger numbers. This is why cooling doesn't cause collapse. The thermal contribution to the pressure is negligible compared to the quantum contribution. Removing the thermal energy by letting the white dwarf cool changes almost nothing about the pressure supporting it. It's worth stepping back and appreciating how remarkable this is. Here we have an object the size of Earth with the mass of a star, sitting in the cold vacuum of space, slowly radiating away its heat over billions of years. It has no engine, no power source, no mechanism generating new energy. By every classical intuition, it should be collapsing. Gravity is pulling inward on every atom. There's no outward force being generated. And yet, it doesn't collapse. It just sits there, stable, permanent, unyielding. And the reason is a rule about quantum identity. A rule that says electrons can't be identical to each other in every way. A rule that was discovered by studying the arrangement of electrons in atoms. A problem that seems completely unrelated to the fate of dead stars. And yet this tiny rule, this constraint on the identity of subatomic particles, reaches up from the quantum world and determines the structure of objects hundreds of thousands of miles across. This is one of the most beautiful connections in all of physics. The very small determines the very large. The rules governing individual electrons determine the fate of entire stars. Quantum mechanics, which was developed to explain atoms and molecules, turns out to be essential for understanding objects billions of times larger. Without quantum mechanics, without the Pauli exclusion principle, white dwarfs couldn't exist. They would collapse, and the universe would be a fundamentally different place. Consider what would happen if the Pauli exclusion principle didn't exist. If electrons were bosons instead of fermions. If they could all pile into the same quantum state. In that case, when a star died and its core contracted, there would be nothing to stop the collapse. The electrons wouldn't resist compression because they'd have no reason to. They'd all happily slide into the lowest energy state, packing together without any quantum objection. The core would keep collapsing, getting smaller and denser without limit. Every dead star would become a black hole. There would be no white dwarfs, no neutron stars either, since those depend on a similar principle applied to neutrons. The universe would be littered with black holes instead of the dim, stable stellar remnants we actually observe. Chemistry would also be completely different because atoms would have no structure. All electrons in every atom would occupy the same lowest energy state. There would be no electron shells, no periodic table, no chemical bonds as we know them. Matter as we know it would not exist. Life as we know it would not exist. The Pauli exclusion principle isn't just an obscure rule of quantum mechanics, it's one of the pillars on which the structure of the physical world is built. Now, I want to be very clear about something because it's easy to get confused here. Electron degeneracy pressure is not a force in the traditional sense. It's not like gravity or electromagnetism, where there's a direct push or pull between objects. It's more subtle than that. It arises from the statistical behavior of a large number of fermions confined to a limited volume. It's a consequence of the distribution of quantum states and the fact that each state can only be occupied once. When you try to compress a degenerate gas, you're trying to reduce the number of available quantum states. The electrons resist this compression not because there's a force pushing them apart, but because the laws of quantum mechanics forbid them from being compressed. Beyond a certain point, there are no available quantum states for them to occupy at higher densities. They literally have nowhere to go. The compression is blocked not by a force, but by a fundamental impossibility. It's as if you're trying to push a ball through a solid wall. The wall doesn't push back with a force exactly. It simply can't be penetrated. The ball can't go through because there's no space for it on the other side. Similarly, electrons in a degenerate gas can't be compressed further because there are no quantum states available for them at higher densities. All the states are full. The gas is quantum mechanically incompressible, at least up to a point. That last phrase, up to a point, is important. And it hints at something critical about the white dwarf's ultimate fate. But for now, let's stay with the white dwarf and appreciate what electron degeneracy pressure means for its existence. A white dwarf is an object held up by the identity of electrons, not by heat, not by energy, not by any ongoing process or mechanism, by identity. By the fact that electrons are fermions and fermions cannot share quantum states. This is a static support. It doesn't need maintenance, it doesn't need fuel, it doesn't consume anything, it doesn't produce anything. It simply is. As long as the laws of quantum mechanics remain what they are, as long as electrons remain fermions, the white dwarf will remain stable. It could sit in space for 1 trillion years, 1 quadrillion years, 1 quintillion years, and it wouldn't collapse. The support is written into the fundamental laws of nature. This means that white dwarfs are, in a very real sense, the most stable solid objects in the universe. Normal matter is held together by chemical bonds, which are electromagnetic in nature. These bonds can be broken by heat, by pressure, by chemical reactions. Buildings crumble, mountains erode, planets can be torn apart by tidal forces. But a white dwarf structure is supported by quantum mechanics itself. You can't break quantum mechanics. You can't turn off the Pauli exclusion principle. The white dwarf will endure as long as the laws of physics remain the laws of physics. There's something almost philosophical about this. A white dwarf is a monument to the quantum nature of reality. It's an object that exists because of rules governing particles too small to see, rules that were discovered by humans only about a century ago. For billions of years before humans existed, white dwarfs sat in space, held up by a principle no one had ever heard of. They didn't need us to discover the principle for it to work. The principle was always there, always operating, always holding up these dead stellar cores against the relentless pull of gravity. We just didn't know about it. And when we finally figured it out, in the early 20th century, it was one of the great triumphs of theoretical physics. the ability to explain why white dwarfs exist, why they don't collapse, why they maintain their size as they cool. All of this came from understanding quantum mechanics and applying it to stellar physics. The physicists who made these connections, Pauli with his exclusion principle, Fermi with his statistical mechanics of fermions, Ralph Fowler, who first applied these ideas to white dwarfs in 1926, they were solving one of the great puzzles of astrophysics. Before quantum mechanics, white dwarfs were a mystery. Astronomers could measure their masses and sizes. They knew these objects were incredibly dense. They knew they were cooling, and they had no idea what prevented them from collapsing. Classical physics said they should collapse. There was no classical mechanism to support them. It took a revolution in fundamental physics, the development of quantum mechanics, to explain how a dead star could resist its own gravity without any source of energy. Fowler's 1926 paper was a landmark. He showed that if you treat the electrons inside a white dwarf as a degenerate Fermi gas, the pressure they exert is more than sufficient to support the star against gravitational collapse. The calculation was elegant and convincing. It showed that quantum mechanics wasn't just a theory of atoms and molecules, it was a theory that determined the structure of stars. The very small and the very large were connected in the most intimate way imaginable. This was a profound moment in the history of physics. It demonstrates that the laws governing subatomic particles have direct, observable consequences at astronomical scales. You can literally look through a telescope and see the Pauli exclusion principle at work. Every white dwarf you observe is a visible manifestation of quantum mechanics operating on a cosmic scale. Today, white dwarfs are among the best understood objects in astrophysics. We have detailed models of their internal structure, their cooling rates, their chemical composition, their evolution over time. We can predict how a white dwarf of a given mass and composition will behave, how hot it will be at a given age, how bright it will appear, what its spectrum will look like. These predictions agree remarkably well with observations. The theory works. Electron degeneracy pressure is not a hypothesis or a speculation. It's a well-established physical phenomenon that has been confirmed by decades of observations of real white dwarfs. We can also study degenerate matter in laboratories on Earth, though not at the extreme densities found inside white dwarfs. Metals at room temperature actually contain a degenerate electron gas. The electrons in a metal are free to move throughout the material, and at normal temperatures, they behave as a degenerate Fermi gas. Their properties, such as the specific heat and electrical conductivity of metals, can be calculated using the same Fermi-Dirac statistics that describe the electrons inside white dwarfs. The physics is the same, the only difference is the density. Inside a white dwarf, the density is millions of times higher than in a metal, so the effects are millions of times more dramatic. But the underlying principle is identical. Electrons are fermions. They obey the Pauli exclusion principle. When they're packed tightly, they generate degeneracy pressure. This happens in metals on Earth and in white dwarfs in space. The physics doesn't change. Only the scale changes. There's one more aspect of white dwarfs that deserves attention before we move on, and it has to do with the relationship between mass and size. In normal objects, bigger means bigger. A more massive planet is larger than a less massive planet. A more massive star is larger than a less massive star. Adding mass makes things expand, but white dwarfs are the opposite. In the world of a degenerate matter, adding mass makes the object smaller. A more massive white dwarf is actually physically smaller in diameter than a less massive white dwarf. This seems completely backward, but it follows directly from the physics of electron degeneracy pressure. Here's why. When you add mass to a white dwarf, you increase the gravitational force trying to compress it. The increased gravity squeezes the degenerate electron gas to higher densities. At higher densities, the electrons are packed more tightly, forced into even higher energy states, and the Fermi energy increases. The degeneracy pressure increases too, enough to balance the stronger gravity. But the balance is achieved at a smaller radius, at a higher density. The white dwarf has gotten denser and smaller, even though it has more mass. This inverse relationship between mass and size is one of the signatures of degenerate matter. It's completely different from how normal matter behaves, and it was one of the first predictions of the quantum mechanical theory of white dwarfs. Observations confirm it beautifully. When astronomers measure the masses and radii of white dwarfs in binary systems where these quantities can be determined precisely, they find exactly this inverse relationship. More massive white dwarfs are smaller. The theory matches the observations with impressive accuracy, but this inverse relationship also leads to something troubling. If adding mass makes a white dwarf smaller, and smaller means denser, and denser means the electrons are packed even more tightly, then there must be a limit. You can't keep adding mass forever. You can't keep making the white dwarf smaller and denser without limit. At some point, the electrons will be packed so tightly, moving so fast, that even the Pauli exclusion principle can't generate enough pressure to resist gravity. There's a maximum mass beyond which electron degeneracy pressure simply cannot support the star. This limit exists, it's real, it's calculable, and its discovery was one of the most important breakthroughs in 20th century astrophysics, because this limit tells us not just how white dwarfs live, it tells us how they can die. The inverse relationship between mass and size in white dwarfs leads us to an unavoidable conclusion. There must be a breaking point. If adding mass makes a white dwarf smaller and denser, and if the electrons inside are forced into higher and higher energy states as the density increases, then at some point the electrons will be moving as fast as they possibly can. They'll approach the speed of light. And when that happens, the physics changes in a way that spells doom for the white dwarf's ability to resist gravity. To understand why, we need to revisit something we discussed earlier about the speed of light. Nothing with mass can travel at or beyond the speed of light. This is a fundamental law of physics established by Einstein's special relativity. As a particle approaches light speed, its effective inertia increases. It becomes harder and harder to accelerate. Pushing it to the speed of light would require infinite energy, which is impossible. This speed limit applies to everything with mass, including electrons. In a low-mass white dwarf, the electrons in the highest occupied quantum states are moving fast, but they're still well below the speed of light. When you add mass and the density increases, these electrons are pushed into even higher energy states and move faster. The degeneracy pressure increases in proportion, and it's enough to counterbalance the increased gravity. The system finds a new equilibrium at a smaller size, but remains stable. But as the white dwarf becomes more and more massive, the fastest electrons get pushed closer and closer to the speed of light. And here's the problem. When electrons are moving at speeds well below light speed, their pressure increases steeply with density. Squeeze the gas a little denser, and the pressure increases a lot. This steep relationship between density and pressure is what allows the white dwarf to respond effectively to increased gravity. Add some mass, gravity gets stronger, the star contracts a little, the density goes up, and the pressure increases enough to restore balance. But when the electrons approach light speed, this relationship changes. The pressure still increases with density, but it increases more slowly, much more slowly. The electrons can't speed up as much because they're already approaching the cosmic speed limit. Each increment of compression produces a smaller increment of pressure. The white dwarf's ability to respond to increased gravity weakens. It's like pushing harder and harder on a spring that's getting softer. At first, the spring pushes back strongly, but as you push harder, the spring's resistance grows weaker relative to the force you're applying. Eventually, the spring can't push back hard enough, and it collapses. This is exactly what happens inside a white dwarf as its mass approaches a critical threshold. The electrons become what physicists call relativistic, meaning their speeds are a significant fraction of the speed of light, and the effects of special relativity become important. In the relativistic regime, the equation of state, the mathematical relationship between pressure and density, changes. The pressure increases with density more gradually than in the non-relativistic case. And this gradual increase isn't enough to keep pace with the increasing gravitational force. The physicist who worked all of this out was a young Indian astrophysicist named Subrahmanyan Chandrasekhar, and his story is one of the most remarkable in the history of science. Chandrasekhar was born in 1910 in Lahore, which was then part of British India. He was brilliant from an early age and deeply interested in physics and mathematics. In 1930, at the age of just 19, he boarded a ship from India to England to begin graduate studies at Cambridge University. The voyage took about 18 days, and during that voyage, Chandrasekhar did something extraordinary. He combined the physics of electron degeneracy pressure with Einstein's special relativity and worked out the consequences for white dwarfs. The calculation was elegant, but the result was startling. Chandrasekhar showed that as the mass of a white dwarf increases, the radius decreases, just as Fowler's earlier work had predicted. But Chandrasekhar went further. He showed that as the mass approaches a specific value, the radius doesn't just decrease, it approaches zero. The white dwarf becomes infinitely dense. The electron degeneracy pressure, no matter how extreme, simply cannot generate enough force to support the star against gravity. There is a maximum mass above which no white dwarf can exist. That maximum mass is approximately 1.4 times the mass of the Sun. This is the Chandrasekhar limit. It's one of the most important numbers in all of astrophysics. Below this mass, electron degeneracy pressure can support a white dwarf indefinitely. The dead stellar core sits in space, stable, slowly cooling, for trillions of years. Above this mass, electron degeneracy pressure fails, the quantum shield shatters, gravity wins. Let me explain why the limit falls at this particular value. The exact number, 1.4 solar masses, comes from a precise mathematical calculation that balances the gravitational energy of a self-gravitating sphere against the kinetic energy of a relativistic, degenerate electron gas. The gravitational energy depends on the total mass and the radius. The kinetic energy of the degenerate electrons depends on the density, which itself depends on the mass and the radius. When you set these two energies equal and solve for the maximum mass that can be supported, you get approximately 1.4 solar masses. The exact value depends slightly on the composition of the white dwarf. For a pure carbon white dwarf, it's about 1.44 solar masses. For a pure iron white dwarf, it would be slightly different. But the commonly cited value of 1.4 solar masses, sometimes written as 1.44, is a good approximation for typical white dwarfs made of carbon and oxygen. The number itself emerges from fundamental constants of nature. The Chandrasekhar limit can be expressed in terms of the gravitational constant, Planck's constant, the speed of light, and the mass of the proton. It's built from the deepest constants of physics. It's not an arbitrary number. It's a consequence of how gravity, quantum mechanics, and relativity interact. Change any of these fundamental constants and the limit would change. In our universe, with our physical constants, the limit falls at about 1.4 solar masses. Chandrasekhar presented his results at a meeting of the Royal Astronomical Society in London in 1935. He expected his work to be received as a significant advance in our understanding of stellar structure. Instead, he was publicly attacked by Sir Arthur Eddington, one of the most famous and influential astrophysicists of the era. Eddington had done pioneering work on stellar structure and had been one of the first scientists to confirm Einstein's general relativity through observations of a solar eclipse in 1919. He was a giant in the field, and he completely rejected Chandrasekhar's result. Eddington's objection was not mathematical. He didn't find errors in Chandrasekhar's calculations. His objection was philosophical. He simply couldn't accept the implication. If there was a maximum mass for white dwarfs, then what happened to stellar cores above that mass? They couldn't be supported by electron degeneracy pressure. They would have to collapse further. But collapse to what? In 1935, there was no known mechanism to halt the collapse of an object above the Chandrasekhar limit. The implication was that the core would collapse without limit, becoming infinitely dense, forming what we would later call a black hole. Eddington found this absurd. He believed there must be some natural law that prevented such an outcome. He argued that Chandrasekhar's use of relativistic mechanics was somehow inappropriate, that the combination of quantum mechanics and special relativity couldn't be applied in this way. He called the result a reductio ad absurdum, a logical impossibility that proved the theory must be wrong. Eddington was wrong. Chandrasekhar was right. The mathematics was correct. The physical reasoning was sound. There is a maximum mass for white dwarfs, and above that mass, electron degeneracy pressure cannot prevent gravitational collapse. But Eddington's opposition carried enormous weight because of his reputation and stature. For years, Chandrasekhar's result was treated with suspicion by many in the astronomical community. Some physicists accepted it, particularly those who understood quantum mechanics and relativity well, but others followed Eddington's lead and dismissed it. Chandrasekhar was deeply affected by this controversy. He eventually moved to the United States, took a position at the University of Chicago, and shifted his research focus to other areas of astrophysics. He didn't receive full recognition for his work on white dwarfs until decades later. In 1983, nearly 50 years after his original calculation, Chandrasekhar was awarded the Nobel Prize in Physics for his theoretical studies of the physical processes of importance to the structure and evolution of stars. The award specifically cited his work on the mass limit. By that time, the Chandrasekhar limit had been confirmed by observations and was universally accepted by the scientific community. But the recognition came late. Chandrasekhar had spent decades knowing he was right, while one of the most famous scientists in the world insisted he was wrong. The story of Chandrasekhar and Eddington is a powerful reminder that science is a human enterprise. Even brilliant scientists can be wrong. Even well-established authorities can reject correct results because of personal biases or philosophical objections. What matters in the end is not who has the bigger reputation, but whose mathematics matches reality. Chandrasekhar's mathematics matched reality. Eddington's objections did not. And today, the Chandrasekhar limit is one of the cornerstones of modern astrophysics. So what actually happens when a white dwarf approaches or exceeds this limit? This is where the story gets dramatic. There are two main scenarios, and both are spectacular. The first scenario involves a white dwarf in a binary system, a system where two stars orbit each other. Binary star systems are incredibly common. About half of all star systems in the galaxy contain two or more stars. In many of these systems, the two stars have different masses, which means they evolve at different rates. The more massive star dies first, becoming a white dwarf while its companion is still a living, hydrogen-burning star. As the companion star evolves and expands, its outer layers can extend close enough for the white dwarf's gravity to pull material off the companion. This material, mostly hydrogen, spirals inward and accumulates on the white dwarf surface. This process is called accretion. Over time, slowly and steadily, the white dwarf gains mass. And as it does, the white dwarf shrinks slightly, becomes denser, and the electrons inside are pushed to ever higher energy states, closer and closer to the speed of light. If the accretion continues long enough, the white dwarf's mass can approach the Chandrasekhar limit, and when it gets close to 1.4 solar masses, something extraordinary happens. The carbon and oxygen that make up the white dwarf's interior, which could never fuse during the normal life of the star, because the temperatures were never high enough, are now compressed to such extreme densities that carbon fusion ignites. But this isn't like the controlled, steady fusion that occurred in the star's core during its lifetime. This is an uncontrolled thermonuclear explosion. The entire white dwarf detonates in a fraction of a second. The explosion is called a Type 1a supernova, and it is one of the most energetic events in the universe. The white dwarf doesn't just explode, it's annihilated. The entire object, all 1.4 solar masses of it, is blown apart in a nuclear fireball that briefly outshines an entire galaxy. A single white dwarf, an object the size of Earth, produces more light for a few weeks than the combined light of 100 billion stars. The explosion produces enormous quantities of radioactive nickel, which decays into iron, flooding the surrounding space with heavy elements. In fact, Type 1a supernovae are one of the primary sources of iron in the universe. The iron in your blood, the iron in the Earth's core, much of it was produced in explosions like these, billions of years ago, scattered across space to eventually become part of the gas cloud that formed our solar system. Type 1a supernovae are also extraordinarily useful to astronomers. Because all Type 1a supernovae occur at approximately the same mass, the Chandrasekhar limit, they all produce approximately the same amount of energy. They all have approximately the same peak brightness. This makes them what astronomers call standard candles, objects whose intrinsic brightness is known. By comparing how bright a Type 1a supernova actually is with how bright it appears from Earth, Astronomers can calculate the distance to its host galaxy with a remarkable precision. It was this technique, using Type 1a supernovae as distance markers, that led to one of the most stunning discoveries in the history of science. In 1998, two independent teams of astronomers used Type 1a supernovae to measure the distances to very remote galaxies. They expected to find that the expansion of the universe was slowing down, decelerating under the gravitational pull of all the matter in the cosmos. Instead, they found the opposite. The expansion was accelerating. The universe wasn't just expanding, it was expanding faster and faster. Something was pushing it apart, overcoming gravity on the larger scales. This mysterious something was named dark energy, and it remains one of the deepest unsolved mysteries in physics. We know it exists because we can see its effects. We know it makes up about 68% of the total energy content of the universe, but we have absolutely no idea what it is. The discovery of dark energy won 3 lead researchers, Saul Perlmutter, Brian Schmidt, and Adam Riess, the Nobel Prize in Physics in 2011. And it all traces back to the Chandrasekhar limit. Without the understanding that white dwarfs explode at a specific mass, producing supernovae of predictable brightness, this discovery would not have been possible. The physics of electron degeneracy pressure, the Pauli exclusion principle, the Chandrasekhar limit, all of it connects in a chain that leads directly to the discovery that the universe's expansion is accelerating. Quantum mechanics, stellar physics, and cosmology are all linked. The second scenario for what happens when the Chandrasekhar limit is exceeded involves stellar cores that are born above the limit. When a very massive star, one with more than about 8 times the mass of the Sun, exhausts its fuel, its core doesn't stop at carbon and oxygen. These stars are massive enough that their gravity can compress the core to the temperatures needed for carbon fusion, then neon fusion, then oxygen fusion, then silicon fusion. Each successive fuel ignites at higher temperatures and burns faster than the one before. Carbon burning lasts about 1,000 years, neon burning lasts about a year, oxygen burning lasts about 6 months, silicon burning, the final stage, lasts about a single day. At the end of silicon burning, the core is made of iron, and iron is the end of the line. Iron cannot be fused to release energy. Iron is the most tightly bound nucleus in nature. Fusing iron requires energy rather than releasing it. When the core becomes iron, fusion stops permanently. There's no next stage, no higher temperature that can restart the engine. The iron core of a massive star typically has a mass well above the Chandrasekhar limit. It might be 1.5 solar masses, or 2 solar masses, or more. Electron degeneracy pressure is trying to hold it up, but the mass is too great. The pressure can't match gravity, and in a catastrophic fraction of a second, the core collapses. The collapse is unimaginably fast. The core, roughly the size of Earth, collapses to a sphere about 12 miles across in less than a second. The outer layers of the star, with nothing to support them, come crashing down. They hit the collapsed core and bounce off, creating an enormous shockwave that tears the star apart from the inside out. This is a core collapse supernova, also known as a Type 2 supernova. The explosion ejects the outer layers of the star at speeds of tens of thousands of kilometers per second, creating an expanding cloud of gas and debris that can be seen for thousands of light years. The energy released is staggering, roughly 100 times the energy output of a Type 1a supernova, though most of it comes out as neutrinos rather than light. And what's left behind after this collapse? If the core mass is between about 1.4 and roughly 2 to 3 solar masses, the collapse is halted by a different kind of degeneracy pressure. Not electron degeneracy pressure, which has already failed, but neutron degeneracy pressure. During the collapse, the extreme pressure forces electrons and protons to combine, producing neutrons and neutrinos. The core is converted almost entirely to neutrons. These neutrons, like electrons, are fermions. They obey the Pauli exclusion principle. They resist being compressed into the same quantum state, and at the incredible densities achieved during the collapse, roughly several 100 trillion grams per cubic centimeter, the neutron degeneracy pressure is strong enough to halt the collapse. The result is a neutron star, an object about 12 miles across containing 1.5 to 2 solar masses. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. Neutron stars are the densest directly observable objects in the universe. They're held up by the same fundamental principle that holds up white dwarfs, the Pauli exclusion principle, but applied to neutrons instead of electrons. The physics is identical, only the particles and the scale are different. But neutron degeneracy pressure also has a limit. If the collapsing core is too massive, roughly above 2 to 3 solar masses, though the exact value is still debated, even neutron degeneracy pressure can't hold. The neutrons are pushed to relativistic speeds, the same problem that afflicts electrons in white dwarfs near the Chandrasekhar limit. The pressure can't increase fast enough to match the growing gravitational force, and there's no next level of support. No other particle can step in. The collapse continues. The core shrinks past the point of no return, the event horizon, and becomes a black hole. A region of space where gravity is so strong that nothing, not light, not information, not anything can escape. The matter inside is compressed to a point of effectively infinite density, a singularity, at least according to our current theories. What actually happens at the singularity is unknown because our physics breaks down at those extremes. General relativity and quantum mechanics, the two pillars of modern physics, give contradictory answers. Resolving this contradiction is one of the great unsolved problems in theoretical physics. The sequence is breathtaking when you see it laid out. Stars with modest masses leave behind white dwarfs, supported by electron degeneracy pressure. Stars with larger masses leave behind neutron stars, supported by neutron degeneracy pressure. Stars with the largest masses leave behind black holes, where no known force can prevent total gravitational collapse. At each step, the same fundamental principle is at work. Fermions resist compression. The Pauli exclusion principle pushes back, but at each step, there's a limit beyond which the resistance fails. The Chandrasekhar limit marks the boundary between white dwarfs and what lies beyond. It's a line drawn by quantum mechanics across the cosmos, dividing dead stars into those that can resist gravity and those that cannot. There's something deeply profound about all of this. The fate of a star, whether it ends its life as a white dwarf, a neutron star, or a black hole, is determined by its mass. And the boundaries between these fates are set by the Pauli exclusion principle and the speed of light. These are not astronomical laws, they're laws of quantum mechanics and special relativity, the physics of the very small and the very fast. And yet they determine the fate of objects millions of miles across, objects that contain the mass of entire stars. The smallest scales of physics dictate the largest scales of cosmic structure. White dwarfs sit right at the heart of this story. They are the most common endpoint of stellar evolution, the fate that awaits 97% of all stars. They are held up by one of the most fundamental principles in quantum mechanics. They slowly cool over timescales that dwarf the current age of the universe. They are, in a very real sense, the most enduring objects in the cosmos. Long after the last hydrogen-burning star has flickered out, long after the galaxies have gone dark, white dwarfs will still be there, cooling, fading, but not collapsing, held up by the identity of electrons, by a quantum rule that was old when the universe was young and will still be in force when the universe is unimaginably ancient. And the Chandrasekhar limit, that boundary at 1.4 solar masses, tells us that this protection is not unlimited. The universe has thresholds, tipping points, boundaries where one set of physics gives way to another. Below the limit, quantum mechanics holds firm. Above it, gravity overwhelms everything. The white dwarf is an object that exists in the space between these regimes, a monument to the power of quantum mechanics to resist the most relentless force in the universe, but also a reminder that even quantum mechanics has its limits. When you look up at the night sky, tonight you probably won't see any white dwarfs. They're too dim to spot with the naked eye, small and faint, hiding in the darkness among the brilliant living stars. But they're out there. Billions of them. 10 billion in the Milky Way alone. Each one is a dead star, a compressed core of carbon and oxygen the size of Earth, slowly radiating the last of its heat into the void. Each one is held up not by fire, not by energy, not by any process or engine, but by the quantum identity of electrons. Each one carries within it the entire story we've explored tonight. The life and death of a star. The war between gravity and pressure. The failure of fusion and the loss of thermal support. And the extraordinary rescue by a principle of quantum mechanics that has nothing to do with heat, nothing to do with energy, and everything to do with the fundamental rules governing the identity of matter. A white dwarf is a star that should have collapsed but didn't. It's an object that classical physics says shouldn't exist. It's a cosmic monument to the Pauli exclusion principle, a visible demonstration that the laws of quantum mechanics reach far beyond the subatomic world to determine the structure of the universe itself. And the Chandrasekhar limit, that precise boundary at 1.4 solar masses, tells us that even this extraordinary protection has an endpoint. Push past it, and gravity wins after all. The universe is governed by thresholds, by critical points where the rules change. The white dwarf sits at one of the most beautiful and consequential of these thresholds, a quantum wall holding back the force of gravity. And understanding that wall, understanding why it exists, how it works, and where it breaks, is one of the deepest achievements in the history of human thought. It connects the behavior of individual electrons to the fate of dying stars. It connects quantum mechanics to astrophysics. It connects the smallest things we know about to some of the largest. And it reminds us that the universe, for all its vastness and complexity, is built on a few simple rules. Rules about the identity of particles. Rules about the speed of light. Rules about how gravity pulls and how matter resists. And from these simple rules, extraordinary things emerge. Stars that live for billions of years. Stars that die and leave behind objects of incredible density. Objects held up by the quantum nature of reality itself. And a precise, calculable limit beyond which even quantum reality isn't enough. That's what a white dwarf really is. And that's why it doesn't collapse. Not because something pushes outward, not because some engine is running inside, but because the electrons that make up its matter are fermions. Because fermions cannot share quantum states. Because the Pauli exclusion principle is absolute. And because below 1.4 solar masses, that absolute rule is strong enough to defy gravity itself, forever.